Hello everyone. Welcome to our video on ML Paper Reading Club. Today we will be discussing about two paper. We will be discussing on two papers. Those are recent trends in deep learning based natural language processing by Tom, Devamanyu, Soujanya, and Erik, and another one is understanding the difficulty of training deep feed-forward neural networks by Xavier and Yoshua. So at first, I will be discussing on the paper named "The Recent Trends in Deep Learning Based Neural Language Processing." So let's just jump into it. So for the beginning, NLP started with traditional machine learning models like SVMs or CRFs that depend heavily on handcrafted features like POS tags, parse trees, n-grams, etc. These features were often sparse and high dimensional, making generalization and scalability difficult. With word2vec in 2013, dense vector representations became standard, giving rise to deep learning dominance in the world of natural language processing. So, what is our goal? This paper mainly reviews the progression of deep learning in NLP, outlining key architectures, mechanisms, and tasks they improve. So, now if we explain the core concepts, the distributed representations. Previously, words were represented by one hot vectors, very sparse, no semantic meaning. Distributed representations, also called embeddings, map each word to a dense vector capturing its meaning based on context. Now, the word2vec or the CBOW or the skipgram learns embeddings by predicting words from a context or vice versa. On the other hand, GLOF uses global co-occurrence statistics. These embeddings allow models to generalize better and reduce the input dimensionality. And the character embeddings tackle rare or the unseen words by encoding subword structures. For your information, the both paper we are discussing today will be available on the post. If you are watching from YouTube, you will find the paper link in the description, and if you are watching this video on Facebook, you will find the paper link in the post. So now if we move on, like at first let us discuss about on the CNNs for text. Like the CNNs treat the text like images. Each word's embedding is like a pixel row. Filters or convolutions extract local patterns, like if you have ideas on bigrams or trigrams. Now, the max pooling keeps the most salient features, like the enabling dimensionality reduction and translation invariance. A dense layer then uses these features for classification. Now you will ask me, like, Himmel, what are the best uses for CNNs? In my opinion, the sentiment classification, spam detection, news categorization, those are helpful. Also, these things you will find on the paper as well. Now if we move on, we have another model, or the recurrent neural networks. Recurrent neural networks, or the RNNs, designed to process sequential input, like ideal for natural language where the order matters. As you can see in the picture, here it is described easily, like RNNs keep a hidden state that evolves with every new word, or we all know the tokens. So what are the problems here? We have, like, each of them have some problems, right? Here the problem is standard RNNs suffer from vanishing or exploding gradients when sequences are long. Now I have two terms to explain to you. Those are LSTM, or the long short term memory, and GRU, also known as the gated recurrent unit. So LSTM is introduced gating mechanisms to control information flow across time steps. On the other hand, GRU, or the gated recurrent unit, is a simpler, faster alternative with similar performance. Now you will ask me again, like, what are they used for and why the paper is talking about this. Like, this model is mostly used for machine translation, like SEQ to SEQ. Also the chatbot response generation, also it is used on the text summarization too. Now I will discuss on one final model, or this is the recursive neural networks. So recursive neural network, or the RNNs, treat all sequences linearly, ignoring the grammatical structure. Like, here you can see in the picture, like, how this thing parses each and every part linearly. It doesn't matter if there any grammatical error or not. The recursive neural networks use synthetic parse trees to guide composition, like how the trees works, we know. Here you can see, like, how this parses in tree structure and following. Each node in the tree computes a vector for a phrase, sentence, or clause. It is excellent at handling negation and compositionality, like not bad and others. Like, and why is this used for? It is mainly used for fine grained sentiment analysis, paraphrase detection, and natural logic reasoning. Now, there are also some advanced trends and hybrid models which pushes the boundaries by combining architectures and introduce new mechanisms. Like, here you can see we have three things also discussed in the paper, which are the attention mechanism, then the memory augmented networks, and finally the deep reinforcement learning. So if you want my personal opinion, like what will be best to learn about attention mechanisms, like, you can see a paper by Google. Maybe the paper titled was "The Attention is All You Need." You can check that paper out. So there they discuss about the attention mechanism in a detailed, versatile way. You can check that out for the detailed perception. Now, in the paper we are discussing today, there are few things discussed on attention mechanism, like allow models to dynamically focus on relevant parts of the input, then like essential in tasks like translation, where each output word depends on specific input words, and finally forms the basis for transformer models. Okay, then if we move on our memory augmented networks, here you can see the combined neural computing with external memory. Also, it helps in complex reasoning and QA tasks where temporary and permanent knowledge must be stored. Now, if we move on to the deep reinforcement learning, or the RL, it is applied in goal directed NLP tasks like the dialogue agents. The model the model receives feedback and learns optimal response generation policies. Like if I give you an example, like there are, if you play a game, you gain a reward once the thing is completed. So if once you get or you complete this on the deep reinforcement learning, it take this as an achievement if you give it a good feedback. Like once a feedback is given on the base of its, is it positive or negative, it create the differences in itself. Now we are in the last of our this paper. Like, as this is not the end, this is, I am in this video I am discussing on the, like, the key points, or what are the key materials discussed on this paper, these both papers. Like, if you look at the conclusion and what are the future directions, the paper here shows how deep learning in NLP has evolved from CNNs to RNNs to more sophisticated memory and attention systems. Also, it shows us the each how each character suits a particular problem, like CNNs for local context, and on the other hand RNNs for sequence understanding. Also, what we discussed, the recursive neural network for the structures. So what are some future outlooks? Like the more like we can see the more hybrid models blending these techniques. Also, we can see the unsupervised sentence representation learning to reduce data reliance, and finally expansion of attention and memory modules into all aspects of NLP, like the retrieval augmented generation, or known as the RAG. So this is the some preliminary talk on the paper, recent trends in deep learning based natural language processing. It is 32 pages of paper. I will be giving the paper link in the description. So I think we can just move on to our next paper. So hello again. Now we're going to discuss on our second paper, which is understanding the difficulty of training deep forward neural networks. So it is key contributions by Xavier and Yoshua. Now here we will be discussed like why deep networks are hard to train, and explain that this paper provides both theoretical insight and practical solution, the Xavier initialization, that is now foundational. Now if we move on, we have some core problem, or the era of pre 2010. So in the paper they discussed why was training deep networks with standard gradient descent and random initialization so difficult, often performing worse than shallower networks. So there are some key explanations by them, I found like that deep networks performed worse than shallow ones despite greater capacity, and they observed some issues like training was very slow and performance stagnated, and training often stalled on plateaus regions of nearly flat loss. So, what were the key hypotheses in their paper? The difficulty lies in how information, the activations and gradients propagate through the depth of the network. Now, we will see some investigations they did on, or they show on their paper. On the part one of their investigation, or they are calling the role of activation functions, they discussed about the most known two activation function, the sigmoid function and the hyperbolic tangent, or the tanh. They explained the sigmoid activation was widely used pre 2010, and they faced some problems, or they showed some problem with sigmoid function, like it's not zero centered, outputs are between 0 and 1. If you if you saw our videos, like our the playlist on word intelligence, where we showed how the sigmoid function and other activation function works. Also, it this leads to saturation, neurons pushed to extremes close to 0 or 1, where gradients become nearly 0, or what we call is no learning. Also, on the other hand, the hyperbolic tangent is zero centered, like it is from -1 till +1, and it performs better. And what were their conclusion on this investigation? They found that the activation function choice critically impacts gradient flow and learning. Now there another investigation, or the investigation part 2, they're calling it the vanishing or exploding gradients. Here a deeper, we can see a deeper theoretical look into the variance of activations and gradients. Like in the forward pass, variance of activations should remain consistent across layers to preserve the signal. Also, in the backward pass, gradients need stable variance to allow early layer learning. Also, what they found were with poor initialization, both gradients and activations either shrink, vanish, or grow, also explode, especially with depth. Now, they showed us some mathematical goals too. They show like they had some goal for stable training, which is the preserved variance across layers for both activations and gradients. Also, they showed two derived conditions, one for forward pass condition and another for backward pass condition. They showed us these two equations. So, what was the problem in their opinion? Like, in their opinion, they thought these requirements contradict unless layers sizes are equal, so a compromise is needed. So once they find this problem, they also came with a solution, or the Xavier solution, also named by the author Xavier Glorot, his initialization. Here they compromise initialization, which ensures that variance remains stable in both directions. So here they set weights with variance and then implemented by drawing weights. So what does this do is this preserves the signal variance, preventing vanishing or exploding gradients, results in faster convergence and better performance in deep networks. Now, what are the key takeaways and the lasting impact on this paper? As this is a smaller paper, like the it is not like the previous one. The previous paper was about 32 pages, and it is a rather than a small paper, in my opinion. Like it is totally in 8 pages. Here they showed some figures and some, also you can see some experimental settings and datasets in the paper. So in my opinion, there are some key takeaways by themselves which I identified. Like they identified that initialization and activation choice were bottlenecks. Also, they showed the provided mathematically grounded goal, like the stable signal propagation. Also, they introduced something called Xavier initialization by the author Xavier Glorot himself, and they influenced all later deep learning frameworks like the ReLU or the He-init or the batch norm. And finally, they paved the way for training deeper, more complex neural networks reliably. So here you can see the visualizing the impact, like how the training is different when we don't use the Xavier initialization and when we use the Xavier initialization. On the left picture you can see the slow convergence, higher errors, but on the other hand, on the right picture there are faster convergence and lower final error. So we can see, like we can tell it is uh, more impactful when we use the Xavier initialization. So to conclude, like it is a foundational step. Glor's paper in 2010, we can like tell it started a different era of neural networks. We seen the pre 2010 era, and now we're seeing the post 2010 era where we can use the Xavier initialization and more like it shifted the community's focus towards principled initialization strategies based on sound mathematical reasoning. Also, their simple, elegant solution remains a cornerstone of neural network. So that is for today. We discussed about 2 papers: one, recent trends in deep learning based natural language processing, and another one, understanding the difficulty of training deep forward and neural networks. As this combining when we combine these 2 papers in a video, it, like if I go through line by line, it this video will take 2 long hours. So I described it in a short pattern, so you can like have the key knowledge of what are these papers are talking about or how they're discussing their things. So also, if you're more like interested about these 2 papers, you can find the paper links in the description below. So thank you for watching, and do follow my page and subscribe to my channel. Thank you so much.